Hello, and welcome to part two of homework 4 here, where we'll be setting up for the main question of part 2 here, where it's write code to demonstrate that with explicit differencing, simulating the temperature profile of a bar with length 20 meters, thermal diffusivity 1, spatial increment of 1, limits the maximum time step to zero point 0.5. And so, um, seeing that it's saying to demonstrate with explicit differencing, we'll be solving this temperature profile of a bar numerically. And let me make sure my phone cam's going. All right, numerically. And so let's start here with writing out this temperature profile, right? To simulate, because yeah. And so let's draw out a bar here. So how do we get to this temperature profile? Well, it's the heat diffusion equation, right, that we sort of derived earlier in part 1. But instead of it being three-dimensional, we only have one dimension, so unidirectional. And because of that, it sort of simplifies our heat diffusion equation uh, by a lot. And later on, there will be some assumptions that further simplify it. So moving on here, what is that heat diffusion equation uh, in one direction? Well, it's the derivative uh, in that one direction, which in this case, it'll be x, the thermal conductivity times that temperature gradient plus heat generation, rho Cp, temperature derivative with respect to time. And so here are two more assumptions. Firstly, is that the thermal conductivity does not depend on position or temperature, and so we can pull that out of the derivative, and that there is zero heat generation within this bar. So it simply becomes, the second derivative with respect to position is equal to, don't forget the K, rho Cp, is that temperature, derivative of temperature with respect to time. And so I'll bring this rho Cp over to get the thermal diffusivity term on the left side, which is alpha. Alpha is equal to the thermal conductivity divided by rho Cp. And so this becomes alpha second derivative is equal to the derivative of temperature with respect to time. So what is this explicit differencing? Well, like I said earlier, it's sort of like solving numerically. We're approximating these derivatives, so to say, um, with their sort of numerical terms. And to do so, it helps to do something called discretization, where we discretize our bar here into sort of segments, so to say. We're turning our continuous variables, let's say position and time, right, into discrete countable chunks. So how does that work? Well, like I said, we're cutting this bar up into segments, right? This distance will be considered as delta x, and after one delta x has passed, we'll have some counter variable move up to 1. After another delta x has passed, that counter variable is at 2. All right, and so we'll say that counter variable is j, and multiplying with delta x will give us our true distance across the bar. And so we do the same thing with time. We'll give it n as its counter variable, and it's for a segment that has passed delta t. And so with that out of the way, let's move on to this actual explicit differencing. And so, like I said, we're approximating these derivatives numerically. And to do so, it's sort of like doing your run-of-the-mill slope, right? Rise over run, that type of thing. So the first derivative will be the slope at whatever points, right? And so let's say this is our original location. j, right? Whatever counter we're at. So at j, and so it will be that'll be our y1, right? So won't write it yet. And so what is our y2 for our y2? Delta y over delta x. And as you can see, delta x has already been defined, so we can just plug in delta x as delta x, but not our delta y. And so it will be y2, so the step after, so t sub j plus 1, right? So t sub j plus 1 minus our original t sub j. Yeah. Like I said, delta x has already been defined. And so this is our numerical approximation. And then that isn't what we need in our formula, our heat diffusion equation, though. So we need our second derivative, and so doing that again, right? The second derivative is the slope of the slopes. So we have our y2, let's say, because this is technically the slope here, and so we'll need the slope back here. So this slope value minus this slope, right, which t at our position we would be the y2, minus the temperature at the position before over delta x, and this is also over delta x. That is the distance between those slopes. And so you can see that we can simplify this expression a bit more. So it ultimately becomes tj plus 1 minus 2tj, because there's 2 minus tj's, and then this becomes plus, because minus minus, and delta x squared. All right, and so we have this term in our expression covered for now. And so next we have the time-dependent one, and that's super simple because it just reflects this first one that we did for position. I wrote for position. So it will be the temperature. What is our y2? Is the temperature at the next time step at the same position. So n plus 1 minus the temperature at that position at our original time, which is just n. And that is over delta t. And so we then realize that at our position here, this is all at the same time, right? So this is at n, this is at n, and this is at n. So we can plug this into our expression, our heat diffusion equation, right? And we will get this. So alpha n minus 2tj n plus 2tj minus 1 n over delta x squared is equal to jn plus 1 minus jn delta t. And so these sort of alpha, delta x, and delta t, we can sort of combine them into one sort of variable that encompasses all their numerical terms, right? And use that as just a multiplying factor across the terms that need them. And so why are we doing that? Well, sort of first off, it sort of complicates the expression by having all these other variables out there that we can control, right? These are sort of custom unit numbers that we can put in, and just having them in one term makes it much easier. And so to prove that we can sort of control all these variables, alpha comes from the material, whatever material we decide to use for this bar. Delta x is the distance step that we decide, so we can make that shorter or longer. And delta t, we can make that shorter or longer as well. And so pulling all those out and onto this left side here, you get alpha over delta x squared times delta t, and I'll make it just some random variable r, and so that will be multiplied by tj plus 1 n minus 2 tj n plus 2 minus 1 n is equal to t n plus 1 n. And so we get to this point and we're wondering, well, what are we actually solving for, right? Which of these terms are we actually solving for? And well, technically speaking, we know every temperature at every position at the initial time step, 0, right? We know, and so we know this value, this term, this term, this term, and this term. The one term that we don't know is the temperature at that exact position at the next time step, which sort of is this term here, right? So that's the whole point of this temperature profile, this equation setup, is to be able to solve for the next time step and, well, eventually just plot all of it, right? Resulting in the temperature profile. And so since we're solving for this term here, we can move this term over to the left and end up with the expression that we'll be using to simulate this temperature profile in our coding portion. So distributing the r, so we get r tj plus 1 n. So we have a minus 2r and a plus 1 of this term. So plus 1 minus 2r of the tjn plus r tj minus 1n. That is equal to tj n plus 1. And so that ends the setup here for part 2. And we'll get into actually answering and showing what happens when we when we try out going beyond the time step of 0.5 seconds here. And so I'll see you in the coding portion here. So welcome to the, I guess, the actual question portion of part 2, over for part 2, in which, well, we'll be writing the code that demonstrates this explicit differencing and simulating the temperature profile. So I have the stuff that we wrote in the setup with our final expression at the bottom here, which I'll be using. And so let's import our usual things here. So numpy as np, and from plotly dot subplots, I think. Imports make subplots. If that's wrong, I'll just look it up. All right, so hopefully that's correct. So how do we start here? Well, let's put in some of our controllable variables that I talked about in the setup, right? So that'll be our alpha, our whatever our time chunk is, or this change in time, whatever we want that to be, and our chunk of position, however big or small we want that, so or change of position, right? So alpha will be equal to 1 point, 1 dot, make it a float. The x, or change of position, will be equal to 1. That's what it wanted in the homework, and will be, or change in time will be 0.5. And then since I created, the arbitrary value variable r with it, I'll have to compute that, which is dt times alpha divided by dx squared. All right, and so we have our controlled stuff out of the way. So what is next? Well, how many divisions do we want in this bar, right? Well, we want, I guess, a maximum of 20, let's say. And so now that we got the main parts of the way, let's actually set up an array that represents our temperature profile of our bar. And this array will be manipulating to get the future, I guess, next time step temperature profile for the bar. And so we need to give this some values, right? And in addition, we are actually holding the opposite ends of the bars at a constant temperature. And so those boundary conditions will stay constant. the temperature there will stay constant at the boundaries. And so what values will that be? Let's say that the bar initially is 20 degrees Celsius. All right. Computer's lagging a bit. Not a bit, a lot. All right, it should hopefully be fine. Let's say the left side is being held at 50 degrees Celsius, and the temperature on the right side is being held at 80 degrees Celsius. And let's say that, oh, right, let's make this array first. So this array, we'll use the np.full function to, oops, t is equal to np.full. It'll fill this array with size 20, right? The amount of divisions, right? And each of those divisions will be inputted a value of the temperature initially, which is T naught. Right, this should be an integer. All right, and that's fixed. So if we look at T, let's say this is J0, 20 degrees, J1, J equals 1, 20 degrees, J equals 2, up to J equals 20, which is 20 degrees. But that's not true, right? We just said that the left and right, so 0 and the last value, are held at these two temperatures. So we got to fix that. And so we can say that T, not bracket, at the first value in that array is T, the temperature at the left side, and the last value is the temperature on the right side. And so -1 is the notation for the last value in an array. And so if we do shift enter and we look at, my computer isn't slow, the temperature, we have that fixed now. So 50 and 80. All right, and so let's actually use our expression that we derived here for the next time step temperature profile. And so since we are holding the two ends, so 0 and -1 constant, the values, I guess you can say that we're actually doing math on, are the values in between those two. And so in between those two is 1 to -1. -1 because it doesn't count that last value. It counts the value before it. And so that will be equal to R times the next position, right? So it will be from 2 to the end. So array notation, you can put nothing there. This is for the temperature array, gotta remember that. Plus 1 minus 2 times R. And that's being multiplied with the temperature at that same position. So 1 to -1, right? The same positions. And then plus R times the temperature at the previous position. So starting at the beginning to the end. The value before the end, which we gotta remember, it's not this value, right? -1 gives us this value, so it's the one before, so it's -2. And so if we do this, and then we look at T again, you can see it has calculated the next time step, and 1 at J equals 1, it has, and J equals, I guess, 19 in this case, has increased by a certain amount of temperature here. And so if we do, if we press Shift Enter again, it'll give us the next time step. And so you can see how this has changed once again. And we can keep on doing that. And it wouldn't get us anywhere because we're not plotting it, right? We can't see this gradual change pictorially, I guess, as a picture, as a graph, right? So that's what we want to do as a graph. And as we can see, we have to keep on running this expression, this equation over and over to get the next temperature profile. So in order to circumvent that issue of manually doing that, we can put it in a for loop. And after ever so many run-throughs, we can plot the resulting temperature profile, and we can get a nice looking temperature profile graph over a certain amount of time. And so let's do that. So I'll cut that. Hello, this is post-editing Ethan, realizing that my audio disappeared halfway through the video, and so time to redo the portion here that got cut out. And so I believe we had just left off right here. We finished coding out our expression. We saw that it worked, and that now we have to plot it and put it in a for loop because we don't want to manually keep on doing the iterations, right? And every now and then we want to plot the temperature profile so that we don't clutter up the graph with every single iteration. And so let's do that. So setting up our variables and expressions and functions for plotting. So subplots. We need a x variable array, right, for our temperature array so that we can plot it. And we want it the same size, right? And so this n equals 20, which was representing our 20 meters because our position step was 1 meter. We want it to be the same size, so we do np.arrange and n, so we make an array the same size of n. And so now add scatter. We want to add the initial state of the bar before we show any of the heating. So y is equal to t, mode is equal to lines, and then we'll do name is equal to f string f0. All right, and so just to show it off like I did earlier, if we do this, we see the initial state. So at dx, 1 dx, so j equals 1, the temperature is 20, and this goes on. So putting that away, let's create our for loop. So for I in range, since we already did 0, which is the initial, we start at 1. Let's go to 1,000 here, 1,000 seconds, right, or however long, whatever unit of time. And so that's doing the iteration. And like I said, we don't want to clutter our graph with every single iteration. And so that was me checking my audio. And so what we want to do here is to put some if statement. Let's say that if this I counter is divisible by 100, so no remainder, that's saying no remainder. If there's no remainder, we'll plot the temperature profile at that counter. So fig dot, I'll just copy and paste this. And instead of this, it will be an f string. So it will be that counter variable, whatever unit that is, times dt. So this I is technically our n, not this n, not the n here, but the n for our from the setup earlier. Yeah, this n is more of our j, and this x becomes our j. So x and n are more of our j, so to say. And so finished. Let's finish that off. And so we want to update the layout so that the graph shows up. Let's adjust the height and stuff here while we're at it. Template. All right, and so this should, oh, I already spoiled this price, but let's change this back to 0.5. And here's our temperature profile. So let's say at 50 seconds, at j is equal to 2 dx's, right? It's at 48 degrees. It's at 48 degrees. And so, like part 2 was asking, demonstrating what we, changing dt around. Let's say we decrease it to, let's say like 2, our time set to 2. Our temperature profile looks all right. So it said why demonstrate that it limits it at 0.5. So let's go beyond 0.5. Say 5.5. And we'll see that, well, it achieves temperatures at realistically impossible, that are realistically impossible, right? 3 times 10 to the 65. But yeah, 65, yeah. That should be it. And so why does this happen? We'll see why it limits at 0.5 in part 3 here. So I'll see you then.